Sunlight is an obvious source and the most commonly used way of generating energy, harvesting sunlight and also storing it in batteries. But that, of course, assumes that you are in the sun, and that is not always the case when you are orbiting the Earth, because at some points, almost every orbit, the Earth shadows the sunlight, and as you can imagine from the temperature I talked about at different planets and different distance from the sun, it has a huge impact on the satellite. Not only the energy source goes away, but the temperature drops rapidly. So this eclipses when the satellite is in the sun, in the shade of the Earth, is a real challenge for a system of solar panels and batteries, obviously. And here you see some example. If you imagine the sun is somewhere here, and in the geostationary orbit, you have a relatively short eclipse period here. It's roughly 30 minutes or 72 minutes per 24 hours. So that's relatively doable. And in low Earth orbit, it's more larger fraction of the orbit that is in eclipse. And since the orbit time here, orbit period, is typically 2 hours, then the cycles number of eclipse passages is much higher than compared to the geostationary satellite. And also to give it a number, when you are in the vicinity of the Earth and are sunlit, the available power to harvest from the sun is around 1400 watts per square meter, which is a nice amount of energy. But this is a simplified image. If we look at the geostationary orbit, it's actually not even that bad, because it's actually eclipses only in the springtime and in the fall, because in the summer or in the winter the Earth axis is tipped like this, and then you avoid the shadow. So here you actually have the sun all around the orbit. And actually the same thing, if I go back, if you imagine this Leo orbit, this is true when the sun is here. But if the sun is here, you, even in this case, can find an orbit where you have sunlight all the time. And that is what is called the dusk-dawn orbit, or solar synchronous, which is popular. So that's the most crowded orbits in Leo is around 800 kilometers sun synchronous, meaning that the orbit plane is slowly turning at the same rate as the Earth. So for the batteries, this means that you charge when you're in the sun, and when you are in eclipse you discharge. And this is also, as of today, one of the life-limiting factors of the batteries. And typically, to to preserve the batteries. If you have a large number of eclipses, large number of cycles, you want to do shallow depth of discharge. You don't want to discharge too much. This you know much better than me, but typically for a LEO satellite which has eclipses, you try to stay in this region, 20% discharge only, and on a GEO satellite you can allow to go down to 80% discharge, simply because the number of cycles is much lower. So I will not go too much in detail on this and related topics, simply because Anna has done it already, and you have the report. This document is one of the deliverables in this project, and you can just look it up and read it, and you find a lot of these discharge cycles. You can find examples of satellites and a lot of details on this topic. In summary, in this document you also see that if we succeed in this project and can come up with a battery which is something like this, and also have actually a higher cell voltage than these have, it would be a substantial improvement to what we have today. And also when you remember, I remember the spec for this project, if we can stand more cycles and a wider temperature range, we have a really good case. So it's definitely something that we would need and want today. I'll steal some information from the document just to give you a teaser before Anna will give you the full picture tomorrow, right? No, later today. Yeah. This is just to give you one example. This is the GOMX-4B satellite, which is a 6U CubeSat. Looks like this. The size is roughly 30 by 20 by 10 centimeters. It weighs some 7-8 kilograms. And it has solar panels mounted on all faces on the body. And I would say this is a quite typical nanosatellite, and today these are popular, and the satellites like this are launched roughly between 200 and 300 per year nowadays. So this is the nanosatellite revolution going on. And a typical power budget of a satellite like this can be from 10 watt up to 30 watt, 40 watt best case if you have deployable solar panels and optimize it for that. But if you want to keep things simple and reliable, you just put the panels on the satellite body, and then in this case we can generate at most around 12 watts, which is sufficient to run the satellite and the payloads. And this satellite also falls under the category of technology demonstration. That's the primary. We have some inter-satellite links on board, software-defined radio, but we also have some actually very useful system, ADS-B, to monitor air traffic, for example. And and this will be launched February 1st next year is the plan. We delivered this in July, and it was ready, and the plan was to launch it in August, but as with many launches, it was postponed a number of months. So it's sitting in Aalborg and ready. I don't want to go in detail here. You can, in the document, you find detailed power budgets. You find more information about the batteries and typical how you operate the systems. For example, this the discharge profile. This is real flight data from a previous COMEX-3 satellite. So you can find things like this, and I'm sure Anna will talk about this in more detail during the afternoon. So that was basically what I plan to say about the most commonly used power system on satellites, solar panels and batteries. But there are of course other systems, and it's if you look, it's a large variety of things, and I will not go through all of them, but I will give you some examples of other ways of generating power in space. And actually one of the most popular ways of generating power, especially when you plan to do missions outside the vicinity of the Earth, is RTGs, or radioisotope thermoelectric generators. And here you have a source, radioactive material on board, and the decay of this is converted into energy by using a semiconductor material. And here is just a list of a number of missions that has been launched, or some of them are actually cancelled. And as you can see, it goes back all the way back to the late 50s or early 60s. So this is an old and well-proven technology to generate power in space. And typically the source is plutonium-238, which is not the same thing as you need to do nuclear weapons. Plutonium-238 is relatively easy to handle, easy to shield, but still it is considered as a risk of having sending radioactive material into space. If the launcher fails, for example, then this thing can come down on us in an unplanned way.